right, Colin, take it away.
Sweet. We're going to talk about activating small language models on Intel Xeon to accelerate business outcomes. So what I'm hoping we all take away from this talk today is a few things. One, how can businesses run AI models that'll drive AI efficiency? Two, I'm hoping to teach you guys a little bit about knowledge graphs and some of the really interesting applications of knowledge graphs and how you can drive more accuracy in AI results from it. I'm also hoping that I can talk to you a little bit about right-sizing the deployment of AI models. And then, of course, because it's Intel Vision, I have to tell you how this all plays into the Intel Xeon space. So I think I'm going to start off. I've got to let you know why you should care about large language models and small language models as well. Obviously, this has been mentioned several times today. I think I heard a couple of people use that buzzword. So it's picking up a lot of steam. It's obviously very important to highlight the contributions of the open source community when it comes to how we're benefiting from all of this. But what I'm going to start off talking about is just a couple of different patterns that are really patterns that we're using right now to drive AI efficiency. So one really interesting but simple pattern that I'll start off with is a pattern called reflection. So this is just the act of having one model first attempt to answer a question and then feeding its work and how it responded off to another model. And so funny enough, just right off the bat, you can see improved performance just from doing things like this. So I kind of highlight a small language model, Intel Xeon, maybe 8 to 13 billion parameters, taking the first stab at that. But that's just one area. Something that I hope to see smaller language models continue to improve throughout 2025 is a second pattern called tool use. And really, what's important with tool use is that you're opening up a whole Rolodex of things for your model to utilize. This could be things like a math engine, a search engine, or just any enterprise APIs. And what's really cool about this is that the open source community has really started to show a lot of like standardization around this approach here lately. So you guys are going to hear a term called MCPs, Model Context Protocol. It's a big thing that's gaining steam. And essentially it's the railroad tracks for how models can interact with APIs, and you're kind of giving them more of that guidelines. So I'm seeing a lot of progress there that I hope continues in 2025 in the small model space as they get better and better at calling tools and doing this kinds of thing. And then, I'm clicking the wrong buttons here. The last thing or pattern that we're all very familiar with is this RAG pattern, right? It's the process of taking your enterprise data, vectorizing it, and storing it into a vector data store so that that can be contextual information that's fed to your model so that you can drive more efficient responses. But what's really cool over the last year is that we started to find that there were even more improvements that we could do in this space. And that's where knowledge graphs came along. And of course, supported by Intel Xeon. So really what that space is all about is about defining further relationships in your data so that you can do sort of a right sizing in some cases of the amount of context that's fed into your, into your model so that it can drive a more efficient response. So there are limitations to how much context is actually good and actually is driving a better response from your AI models. So I'll dig into that a little bit further. But maybe before I move on, I should just comment that I'm really looking forward to Intel Xeon 6. I think what the messaging we're getting across the board is that we're going to see improved vector performance, improved inference for small language models there. So 2025 is going to be very interesting. So I'm going to maybe dive in a little bit further about knowledge graphs and how they actually drive some of that accuracy. And so I've definitely simplified part of the approach here. But what's important is that we're all familiar with taking your enterprise data, creating some of these vector embeddings and storing it. But at the same time, what can really drive some of that efficiency, like I'm saying, or like I was saying before, was you capture some of these inputs on how that data is related to other data, and you store that into a graph database. So there's obviously a number of use cases for knowledge graphs, but this was just an interesting space that, combined with RAG, we've seen drive a lot of accuracy. So what's really cool is that these foundational models, and any model really that's a text generation model, has begun to respond really, really well to these types of inputs. So for applications where the kind of tolerance for bad responses is incredibly low, this has been a real focus area to get those extra percentage points and extra value out of your data. So I'm going to dig into a specific use case around reducing the advanced network the burden of advanced network troubleshooting with AI-generated knowledge graphs. So that is a mouthful. So it's going to take a minute to kind of set the stage for this one. But really what we had here was a client who deploys networking solutions for their customers. And as you can imagine, if you have a team of engineers that are ready to support and you have a customer calling in about having a serious network issue, you've got a big problem on your hands. And it needs to be resolved very quickly. So what was interesting about this use case was that the team had a ton of tribal knowledge that we had a really a tough time nailing down and trying to actually immortalize some of this information. But the other thing was that they were already using complex graphs to capture a lot of the information about these deployments. So what was really cool is that we utilized a knowledge graph and small language model solution, mostly deployed on Intel Xeon, and also supported by OPIA accelerators to quickly deploy Neo4j for our use case in order to accelerate this. And the result in the end was that we were able to drive a 10 to 20% reduction in the overall network troubleshooting time for that team. So if you've ever worked in like field operations, that metric is mean time to response or mean time to resolution. That's really what we were digging at, and we were really happy with the outcome here. So maybe I'll break this down a little bit further and talk about some of the areas that we honed in on and focused on. So the situation starts with, obviously, a customer has an issue. They reach out to the network troubleshooting team, and this platform tool that we were able to work with them to create would take a set of unstructured network router data. It would chunk through it. It would construct a graph. And then we were able to put to use the other graphs that are field graphs that they were using and do a graph similarity analysis so that we could basically immediately get these guys on the right track, identify the issue so that we could reduce that time that it took for them to get to work and get to the right space. But what was also really cool was I mentioned a little bit about tribal knowledge, and the back half of this workflow was really focused on trying to codify a lot of the information that the lead engineers already knew, about certain situations. So we were able to take, some of their tribal knowledge combined with advanced network troubleshooting documentation on certain situations, and we're able to use that in a pretty what is now standard RAG kind of workflow to aid these engineers. So What was really cool about this is that we didn't need to use giant models, a small language model for the way that we were, set out, that the way that we set out to use this or to cover this use case was enough here. And so I kind of have challenged everyone to kind of right size the model usage and think about what kind of hardware you're deploying these models to. Because sometimes I've seen people, I guess I've heard the phrase, use a bazooka to hunt a fly. So in 2025, I will challenge you all to do more with less and try to explore how you could right size AI usage. Thank you.
Right. Thank you so much. Let's give Colin a round of applause. Who has the first question? Yes. Okay, let me tell you. I'll start you and then you. The secret is when you ask a question, you count to 7 in your head because that's the average amount of seconds it takes someone to formulate a thought. And so if you're in sales, wait 7 seconds. Don't cut them off. That was an extra tip.
It's a good tip.
Thank you. Thank you very much. So my question is, in your graph diagram, you were using some vector DBs. May I ask, how do you benchmark the accuracy of different vector DBs?
Yeah, we've done a lot of that. Do you maybe have is there anything specifically that you'd want to benchmark other than throughput per second? That's obviously an important metric. We obviously will try to benchmark based on concurrent users and that kind of thing, and then latency as well. But is there anything else that that's not typical?
The end result is the elimination of hallucination, right, and increase the accuracy. So I was interested to see if there is any benchmarking that you guys have done, and it's publicly available. We are an alternative to vector DBs, so that's why I'm interested to see what's out there and what you guys have done.
No, I'm very interested to hear more. Maybe you should come by the booth. I don't know if I probably have a lot I need to learn from you. So, thank you.
Hi. So I was curious to get your perspective on where do you tip over from a CPU-based to a GPU-based modeling for your customers. So do you have a characterization of what is the threshold at which a CPU-based inferencing model reaches its limits and you recommend a GPU? And the second part of the question I wanted to get your take on is, how are you utilizing OPEA and the reference architectures of the recipes provided in there to build out your reference architectures or your playbook with the customers?
Both great questions. Yeah, so just being completely realistic, anything that's beyond 8 to 13 billion parameter model, you're probably leaving the CPU space. But then the other dimension that you've got to look at is the size of the context that you need. That can really slow down a CPU from what we've seen. So if you've got a use case that needs every iteration or every inference request has a very large context window, that's probably when you're going to go look at a GPU there. And then the second question, how do we utilize OPEA, was it? So we've tested and utilized a number of the blueprints that they have available. So they're, it's obviously all open sourced. Anybody can go to GitHub and grab some of that. In this particular use case, it was our Neo4j, GraphDB implementation, that we utilized as our blueprint starting point.
Thanks.
Yeah, thank you.
All right, who's got another question? Anybody got one last question?
I spoke kind of fast. I chunked through that.
No, you're good.
So.
You're good. A couple housekeeping things. If you guys have more questions, you can check out all of what Accenture's got going on there. We have a couple more presentations at the top and bottom of the hour. And then again, if you want to watch the presentation again, or there's other presentations that you want to watch that you haven't seen, go check out Intel YouTube, Intel Business YouTube channel. On all of them will be uploaded by the end of the week. So thank you guys so much. Let's give Colin a nice warm round of applause. Thank you very much, sir.
Thank you.